Cool. So we'll get started. We do have quite a lot of slides, and so we'll be moving pretty fast today. And so we are taking questions at the end, and so feel free to ask us more questions if we don't clarify enough. So hello, my name is Andrew Ho. I am a product manager for the machine learning infrastructure team at Airbnb. I am joined by Krishna, who worked on the machine learning infrastructure at Airbnb as well. And we're here to talk to you about Bighead, which is Airbnb's end-to-end machine learning platform. And so to start off with, it's good to talk a little bit about the history of why this began, the formation of our ML infrastructure team. In 2016, Q4, there are only a few major models in production, and in general, models were taking on average about 8 to 12 weeks to build as well as get into production, and so it was taking quite a lot of time. Everything was built on Aerosolve, which is something that we've open sourced, Spark and Scala. There was no real support for TensorFlow, PyTorch, sklearn, or other popular ML packages. There was significant discrepancies between offline and online training. And so with all of these challenges that was already there, the ML, the machine learning infrastructure team was formed with the charter to enable more users to build machine learning products at Airbnb. We were looking to reduce the time and effort it took to build your ML models, as well as enable easier model evaluation. So before the machine learning infrastructure team, as well as the whole Bighead, what was there at Airbnb? So Airbnb had a couple of things that were already using machine learning, which was search ranking, smart pricing, and fraud detection. What generally happened was there had to be a big enough need to actually establish a large enough team to start building some of these things out. So the real kind of goal that we're looking for is essentially how do we put machine learning into different aspects of Airbnb where we can't afford to get a massive team up and running. And so you can imagine that the potentials of machine learning at Airbnb are quite high. Paid growth is one of them. Classifying listings is another. Room type categorizations. We actually recently released a blog post on this, and so feel free to check it out. We were able to do a lot of classifications on different images of room types so that we can make sure that when you're on Airbnb, you can see the best photos of the homes and so that you can see everything that's great about it rather than just getting a lot of pictures of bathrooms or just someone's garage. And so there's a lot of potential for machine learning at Airbnb, and these are just some of the things that we're looking to do. So what's the vision of the machine learning infrastructure team? The vision is to have Airbnb routinely ship machine learning features throughout the entire product. And our mission is to equip Airbnb with shared technology to build production-ready, and that's actually key for us, really getting into that production-ready state. And production-ready ML applications with no incidental complexity. And so for those of you who don't know, there's intrinsic as well as incidental complexity. Intrinsic complexity is just if you have a difficult problem, really putting your minds to it to solve it. And then incidental is all the other complexity that comes with it on the side. And we found that there was a lot of incidental complexity, and so how do we reduce that? And the technology we provided was in tools, platforms, the knowledge, sharing feature data with everyone else. And so the value of having a common machine learning infrastructure at Airbnb was to remove incidental complexities by providing generic reusable solutions. And so how do we build out a platform so that different teams at Airbnb can leverage this so they can make production-ready models? How do we simplify the workflow of a data scientist as well as machine learning engineers? What kind of tools do we provide to them? What kind of libraries and environments to make them more efficient and reduce that development lifecycle, which I mentioned before was about 8 weeks to 12 weeks to get done. And at the same time, we're looking to establish a standardized platform across the entire company so it's easy to share all this information with one another. We found that Airbnb, a lot of people were dabbling into machine learning. So how do we make sure that if you're building something new and innovative, you're empowered to do it, as well as if you're repeating someone else's work, that you can actually see what they've done and iterate on that. And lastly, one of the key things we're looking to do is make it easy to do the right thing. And so having a unified machine learning platform, we're able to standardize a lot of the best practices. So the motivations. So Q1 2017, we're figuring out what to build. So we've talked to quite a lot of teams at Airbnb to really figure out what the needs were. We talked to many data scientists and machine learning engineers. Some of the learnings were we didn't have consistency between machine learning workflows. New teams were struggling to begin using ML, so there was a high kind of upstart time. Airbnb had a wide variety of machine learning use cases that were really untapped. Existing machine learning workflows were slow and fragmented. Incidental complexity was incredibly high rather than the intrinsic complexity of what people were doing. And everyone really thought of machine learning as a linear process. However, we want to bring this kind of cyclical mentality to machine learning, and this is what we found that a lot of the people were doing. And so essentially, it went from data management to training your data, or training your models, productionalizing it, and then your model management and monitoring, and then it iterates back over and over again until you're happy. And so we found this kind of cyclical approach where people kept repeating these steps, and so we want to make this as efficient as possible. And so what we are providing is that inner piece, which is the core machine learning and feature engineering. And we actually have, I think, 6 services. I can double count that later. But within the Bighead infrastructure, we actually have a number of components, which are Zipline, RedSpot, BigQ, ML Automator, Deep Thought, as well as the model repo, which is really there to streamline this process to make it more efficient for data scientists and machine learning engineers. So the architecture, some key design decisions. We wanted a consistent environment across the stack, so we used a lot of the Docker containers. We wanted consistent data transformation, common workflow across different ML frameworks. This was one of our learnings early on, that we want to support a lot of the popular ML frameworks so that individuals can leverage what they already know, as well as learn the popular technologies out there. And that includes scikit-learn, TensorFlow, PyTorch. And we wanted modular components. This made it easy to customize, as well as it made it easy to share data and pipelines across the company. There you go. Bighead architecture. So this is what the architecture actually looks like underneath the hood. We'll talk a little bit more about most of these services. I won't go too much into Zipline, just because I've given a talk yesterday on Zipline, and because of time, we want to make sure that we're constantly moving. So this is underneath the hood, what's going on in the orchestration for Bighead. But from a user's perspective, it really comes down to using RedSpot. And so RedSpot is our kind of Jupyter hub, which helps you use your Jupyter notebooks. And this is kind of the user flow. So users will go to RedSpot, use Jupyter notebooks for their models, put it into Git, and then everything else is orchestrated by Bighead into getting your model into production. And so these are the components that I mentioned before. For data management, we have something called Zipline. For training, we have RedSpot and BigQ. Core ML library is ML Pipeline. Productionization is Deep Thought, as well as ML Automator. And then model management is the Bighead service. So as I mentioned before, we won't really dive too deep into Zipline just because of time. But feel free to watch our previous Spark Summit session, which we talked about it in depth, if you want to learn more about Zipline. So RedSpot. So RedSpot is the component, the earliest component in the user workflow for data scientists, as well as ML engineers. They'll most likely go through RedSpot. Oops, I skipped a slide. So why did we build RedSpot? We actually started with Jupyter Hub, which is an open source project and helped manage multiple Jupyter notebook servers. But there are a couple issues that we've encountered, and we had to go build out something separate because of that. And so some of the issues were, a lot of our users were installing packages locally and creating their own virtual environments. Unfortunately, that leads to a lot of fragile environments. Other users wanted to use Jupyter Hub on larger instances or instances with GPUs, and it didn't really have that customization. And users wanted to share their notebooks with teammates, which is very common, and I'm sure it happens everywhere else. People want to share their work with others. And lastly, we wanted to make sure that this is failure resistant, tolerant to failures, and so we wanted to make sure that we had this kind of persistence, which Jupyter Hub didn't really provide us. Containerized environments, and so everything is containerized via Docker. This allows us to customize the notebook environment without having to affect other users. It makes it much easier for us to install system as well as Python packages, and it's easier to restore state, which helps us reproduce things much faster. It has support for custom Docker images and the base images based on what the user's needs were. And so if you wanted GPU access or pre-installed machine learning libraries, you can choose that. And so this is actually kind of the front page at what people experience. So you can see this is RedSpot. And from here, you can choose whether you want Essentially, there's two options, containerized environment or remote Docker. It's not really a containerized environment, it's more of a shared environment. And so we have shared instances and dedicated instances. And I'll talk a little bit more right after that. And then you can change your base Docker image, the configuration you want to begin with. So for the remote instance spawner, like I mentioned before, there's dedicated instances. And so if you want to get a bigger machine, then you can actually specify that. And so it gives you more power for bigger jobs, as well as total isolation, because you have your own machine. And the nice thing is it's just not shared by other people, as well as there's a form of garbage collection that we do. So if your machines are idle, then we'll periodically terminate it, just to save on costs. Here's the architecture for Jupyter Hub. And so, not Jupyter Hub, Red Spot. It uses Jupyter Hub. We've actually forked it. And then as a Docker daemon for some managing the containers. And then you can see we have the remote instances as well as the shared instances, which is that middle piece right there. And then we use MySQL for some of the system metadata, EFS for persisting a lot of the notebooks long term to make it resistant to failure, as well as the data backend, which is S3, Hive, Presto, and Spark. And it can connect to any of these to pull in the data that you want. Okay. So Red Spot summary. So what is Red Spot, right? It's just a multi-tenant Jupyter notebook environment. It makes it easy to iterate and prototype machine learning models. It was improved upon the open source version of Jupyter Hub. It can be containerized. It has a remote notebook spawner for dedicated instances in case you want your own machines. It can persist the notebooks within EFS just to make sure that it's resistant to failures, as well as it can revert to prior checkpoints. And currently at Airbnb, we have 200 plus weekly active users, and this is constantly growing. Awesome. So next part, Krishna will take over.
Cool, thanks. So once you log into Red Spot, spin up a container, so you end up with this Jupyter notebook in the container, which has this Python library called Bighead library. So why did we build it? So as we talked to users and learned about various ML use cases, we quickly figured out, okay, there were various transformations that a lot of users were sort of rewriting again and again in slightly different ways, and it was sort of buggy and inefficient. And two, users were doing a lot of last mile data transformation in the model, as part of the model. And there were no real good abstractions for doing that. Large-scale multi-row aggregations happens in Zipline, right, in the warehouse. And then you load the data, and then you do last-mile transformations like scaling, imputing, and so on. So there were no good abstractions for that. And so it was easy for users to write it in different ways. So it was hard to share knowledge, and it was leading to a lot of confusion. And especially if you want to run your code in GPUs or CPUs, then again, you have to think about how to make it efficient. And some of the code was inefficient as well. And there were no good visualization, especially if you have to do multiple transformations in a chain on a particular input. So we wanted to figure out a way to provide a library which addresses many of these problems. And finally, when you load the training data, we also wanted to make this library identify data issues like surface missing values or values that you didn't expect, and so on in a nice visual way. So this library is basically consolidated pre-existing transformations, hundreds of them, with proper unit testing and fixes and stuff like that. And then we build this ML pipeline abstraction where you can take your input, provide a DAG of transformations on top of that. And this pipeline basically maintains metadata about various transformations that have happened. And in the end of this pipeline, you can drop in your model code. And then when you plot the feature importance in the model, it shows you what feature went through what transformations. It's very easy to track that. So we implemented data parallel and feature parallel transformations. So it made things much more efficient. We automatically figure out whether you're running on GPU and CPU, and then use the right underlying libraries. And so we also implemented wrappers around common framework like scikit-learn, TensorFlow. So you can basically embed these libraries as a last step as a transformation in the pipeline. So let me give an example which will make this much more concrete. So here is a model that is built on census dataset. So basically we categorize the fields into categorical and numerical, and then we instantiate a pipeline object, and then we say, okay, take numerical and apply mean imputing and then scaling on top of this. Take categorical fields and then do one-hot encoding, and then take all of this stuff and then send it to XGBoost classifier, and then return the pipeline object. So you can then take this pipeline object and call fit, transform, and then serialize and store this trained artifact. So you can also plot the pipeline and see, how the data, what sort of transformations is happening. In this case, it's doing a serial transformation, but you can slightly change it and also make this transformation in parallel. We run it on different CPUs and make it faster. And finally, once you fit and plot the feature importance, so it shows you, okay, final weight is like the most important feature. It went through these set of transformations. And this works across XGBoost, TensorFlow, and all the other libraries that we have integrated into ML pipeline. And like I said, so it's, you just call serialize, it packages everything, all the trained artifacts, weights, everything. It produces a tar.gz where you can store it in Bighead service or model repository, and then you can deserialize it anywhere else in the same Docker container, and then use it for offline scoring or online scoring. So this is the final bit about the training data visualization. So you can say, okay, show me the stats about training data and test data, and then it's a React component which just renders in Jupyter Notebook. It shows you some sample data, and then it shows you various visualization of the data, like histograms for categorical, box and violin plots to identify anomalies, like cases where you have these extreme values and so on. So you can look at it and say, okay, this field doesn't look right, maybe I should remove it. And so you can go through this actual modeling process. In the side, it also shows you this correlation analysis, which shows which fields are correlated, which ones are not, and so on. So this is a bit about, so now let's say you have this pipeline which you fitted and then you saved. Now, one of the most common things you want to do next is to use that model for online scoring. So that was a pretty common use case. And so we built a service called Deep Thought. It's in the right-hand side in the top of this architecture diagram here. And so the reason we built it is the following. So what we had seen is various product teams rolling out their own services for online scoring. It was not production ready. As you scale, it used to fall down, and there was no proper monitoring, alerting, very standardized issues that we used to see. And two, many times we saw that data scientists were sort of gated by engineering time to put their model into production. So we wanted to basically solve these sort of inefficiencies. So the second class of problem that we saw in this process was that there were subtle differences between offline scoring and online scoring, and so it was very hard to track down. Usually it fell into sort of three categories. Inconsistencies because of software issues, you installed a slightly different version of a particular package, or inconsistencies in the transformation. Offline transformation was done in Python, and then online was done in, say, Java, and then implementation differences led to various differences in transformations. Or finally, it was because of data discrepancies. In offline, HighView computed a particular field in a certain way. In streaming, it was computed in a different way, which led to problems, right? So by using Docker, we sort of eliminated the software inconsistencies. By using this Bighead library, we sort of eliminated the transformation inconsistencies. And then by using Zipline, which automatically generates the Hive and the Flink jobs for you, we sort of eliminated this streaming versus offline data inconsistency issues. So looking, so where we ended up with is like a Deep Thought is basically a Java service. It takes the ML pipeline that was serialized in the previous step. It can load it inside a Docker container. It gives you a service, Java service around it. It's very easy for anyone to make a deploy, scale up the service, scale down the service, deploy, undeploy, and so on. It gives you a REST endpoint, so all the other Java, Ruby services can connect to it and get the score. So whatever data we have in the warehouse gets loaded into key value store, so it also talks to the key value store, loads the features from that. And then it implements standardized logging, alerting, dashboards, provides isolation, and so on. So this is one of the highest QPS service we have at Airbnb. It has hundreds of models, and it's scaling pretty well. So if you look a little deeper, this is sort of the architecture. We have this Java service REST endpoint. It has a model manager where it manages various Kubernetes pods. Within each pod, you have like we have a Docker container which runs a Python server, which loads this ML pipeline object, and then the REST endpoint gets the features to score, sends in the features to the Kubernetes pod, Docker container, Python process, gets the score, sends it back to the client. This is more a breakdown of how the data is actually flowing through, what sort of transformation is happening. Again, REST endpoint, Java service takes it, sends it to the Kubernetes pod, which sends it to the Python process in the Docker container, and then gets the scores and sends it back up. So the last part that I'll talk a little bit about is this Bighead service. So the reason we built it is that we found that model management was a fairly tricky problem. So there was no single source of truth for understanding all the changes that have happened to a model, config changes that have happened to a model. We had seen many cases where models were put into production from after training on like developer machines or data scientist machines, and then if someone wanted to improve on that, there was no code, there was no proper we don't know what code was running there, so the artifacts were not tagged with proper Git SHAs. And also monitoring was fairly tricky because some part is monitored in the Java service, other parts are other data is monitored in the warehouse. So having a single place to understand the end-to-end health of the model was pretty important. So we built this service called Bighead service, which is at the which is at the center of everything. This is the piece that basically connects everything. So after you train your model in Jupyter Hub, you register this model in this Bighead service. So this is the repository of both trained and untrained models. And for a particular model version, you have various different training runs, which we call as model artifacts. And you can deploy specific model artifacts, and then we have continuous monitoring of the Kubernetes pods, the health of the data, and everything linked together in the single UI. So this is a single UI for deploying models, monitoring the health of the models, and then even experimenting, splitting traffic to different versions of the model, and so on. So this is a quick GIF of how it looks. If you go to this Bighead UI, you pick a model version, and then you see different model artifacts or different training runs of the model, and then you can deploy a specific training run, which we call as model artifact. And then if you have online scoring, then you get links to the Kubernetes dashboard where you can look at the CPU usage, memory usage, and so on. So to quickly summarize, so in Airbnb we have like a wide variety of machine learning use cases. So we wanted to address the incidental complexity that Andrew talked about, which a lot of engineers and data scientists went through in building and managing machine learning models. So we started building this end-to-end infrastructure on top of various open source technologies like Spark, Jupyter, Kubernetes. What we discovered was that there was various gaps in having this end-to-end machine learning platform. So we have built out various pieces to plug these gaps. We have like a generic online scoring service. We have Zipline for feature generation and feature management. We have the Bighead library for feature transformations. And then we have various visualizations on top of that. So we have built out these various components to actually build this end-to-end machine learning platform. We are aiming to open source this soon, and if you have interest in it, reach out to Andrew, and this is his email. Thanks.
Awesome. So for the last 5 minutes, we'd like to take any questions that people might have about the service. I know that we've kind of sent a lot of information to you guys.
Hi.
Yeah. So let us know if there's any questions.
Thanks for the talk.
Oh, okay.
Obvious question, Bighead, is it from Silicon Valley?
Yeah, it is.
Okay. What is your metadata store? What do you use
Metadata?
to store all your metadata? Where do you
Oh,
store?
yeah. The metadata is not huge. We just store it in the MySQL instance.
Oh, okay.
But the feature data gets stored in Hive.
Okay.
That's much larger.
Okay. Thank you.
Oh, yeah. Question?
So,
Right. So the shared, there is a shared machine, which is the X1 machine, which is really large. When users log in, they can either choose a shared machine. The container runs in the shared machine with standardized like 20 CPUs and 120 GB of memory and so on. But if you want truly dedicated instance because you're doing some benchmarking or you want to use like 8 GPUs or 4 GPUs or whatever, if you have some custom requirements, then you would choose remote instance and then we would spin up a different instance for you.
So one question regarding the architecture. Is it secure? Do you have integration with Kerberos or anything?
So the warehouse is secured. So all the clients, so when we access data from Hive or any warehouse, there is proper authentication and authorization implemented. It's not Kerberos, we have something different, implemented something slightly differently. But all of that is, yeah. When you log into RedSpot again, you are authenticated. We have internal systems called for authentication and authorizations.
So do you have something specific for the notebook authentication or no?
So all of these services are behind something called internal auth, which is like a Airbnb-wide service for authentication.
Okay, thanks.
Yeah.
Is she waiting first? Yep. I think she might have been first. Yeah, question over there.
Go for it. So it's about 10 people now. Yeah.
Hey, thank you for the good presentation. My question is, have you faced a situation where your data scientists go in and then say download models out of GitHub or out in the internet, and how do you validate it before you productionalize it? Is that the responsibility of your team to ensure that the model that they have developed would be scalable in production environment and supportable in the production environment? I think you briefly touched about having the code for it, but is there a way you can validate it and ensure that?
Right. So testing the model, the quality of the model is really up to the users. So we have like staging environments where you can go, put your model into like deep thought staging boxes, send traffic, and collect statistics. But optimizing the model and monitoring the health and reacting to the alerts is really up to the users. We provide the infrastructure, and the users have to take care of their models.
And licensing and other legal details of models downloaded from out of the internet or GitHub, it's also...
That's up to the users, yeah.
It's all users, you just
Yeah.
provide the platform.
Yeah.
So, okay, cool, thank you.
Yeah, thank you guys for the talk. 2 questions. So first is the model deployment or development. I saw you only had Python models. So is there any other technology that you support apart from Python, or you have
So right now we
limited-
only focus on Python.
Okay.
But because we run stuff inside Docker, so for example, online scoring. So the expectation is that there's a web server with a specific API. So we could implement other languages, but right now we wanted to like get the end-to-end stuff working in one language first before we focus on other languages. Right now it's purely Python.
And the second is on the Jupyter Notebook, okay? So are you using like a remote spawner where the kernel runs, or are you spawning the entire Jupyter Notebook remotely?
So it's a custom spawner that we implemented, and the way so basically the way it works is we have some internal services for spinning up a AWS instance. So first it does that, and then it runs the Docker daemon, and then spins up a Jupyter Notebook inside that.
Okay. Thank you.
So it's like Jupyter Hub is centralized, but Jupyter Notebooks are either remote or local.
So basically, a user would actually connecting to a Jupyter Notebook URL to spin up the notebook.
Correct.
Okay.
So user would once you just log into RedSpot, that's all they see. And behind the scenes, it's either local Docker or remote Docker. It's all handled by us.
Okay. Thank you.
So we're out of time. Please find the speakers offline for additional questions. Thank you, Andrew and Krishna.